Hello and welcome back. Okay, previously in the I/O series, I added some input and output lines to the system, and then we used those to interface a couple of SPI devices by bit banging the protocol. Now, what I'd like to do is get a higher data throughput to the system, and that's going to mean we need to build some actual circuitry for at least assisting with the SPI protocol. So let's take a look at what we've got, the code we wrote, and then we'll see what we can do about optimizing that. So here's the I/O boards. We've got 8 bits of input. We're only using 1 bit at the moment, and we've got 8 bits of output, and we've kind of got that plugged into a few different things to implement the SPI interface. Let's power it on. So I'm going to run the time code. This is going to read from the real-time clock, and I'm running this at 8:48. Bang on. Now, I did set the clock again a few days ago, so I'm not surprised it's pretty close, but that looks like it's holding time reasonably well. Now, each of these SPI devices is connected up by 4 lines plus power and ground. Now, firstly, you've got the chip select line. Now, we've got a different one of those going to each device, but then we have common lines, which are the clock, data in, and data out. And I think those 4 signals are a good way to separate out the functionality as we try and build bits of circuitry to help us along. Here's the code for the program I just ran to read in and display the time. Now, this version of the code is reading 8 bytes from the RTC all in one go. It's kind of cool, actually. I don't think I've shown this before, but I did unroll the loop, and then I ran through this whole section of code 8 times to read all the bytes from the device I wanted. Now, the individual bit loop is here, and I've unrolled that 8 times, but we've got an immediate load, which is going to be 2 cycles, out, sub, out, in, shift right, shift left. These are all 1 cycle instructions. So that's going to be 8 cycles per bit. We multiply that out by the 8 times we've unrolled the loop, 64 cycles, and then storing the byte and looping back is going to add an additional 8 cycles. So we've got a total of 72 cycles per byte. Now here I'm setting A with a combination of bits inverted, and that's because the way chip selects work are a little bit of an annoyance. These are actually active low lines, which means as I use additional lines for each new device, I have to make sure that that line remains high all the time I'm not using it. So I kind of started off by solving that problem by setting every bit on the output and then unsetting them as I was using them. But that's actually going to be a bit of annoyance as we go, because we've got a total of 8 bits, so we're capped to 8 devices minus however many additional control lines we need. So I think this is the first place that would benefit from a small amount of extra circuitry to help us both avoid contention of multiple devices selected, but also expand the number of devices we could theoretically attach. And I think regular viewers of the channel will know exactly what device I'm going to go to for that. I'm going to use a 138 328 line demultiplexer chip. Now, when I was first looking into all the various parts I had for building circuitry, I got quite excited about this one and made a video devoted to it because I knew it was going to be very handy in a lot of different circumstances, including this one. So let's jump to the circuit and see what we can do. Okay, so I've got one of these devices. Power and ground. Now this chip will take 3 bits of input and decode that to 8 active low enable lines, 7 across here and 1 here. Now I could take the 3 address lines and drive it from 3 of the data output lines, and that would work, but we would have to reserve 1 of the 8 lines to be the nothing selected input. So I'm actually going to pretend we've got 4 bits of address and use one of the enable lines to provide that extra. So with just the one of these chips, we have indices 0 through 7 produce no output, but 8 through 15 will produce 8 usable active low enables. So let's take out those chip select lines. And then that top bit goes into the active high enable, which is that one. These 2 are active low enables, but we're not using them right now, so I'm just going to pull them down. So the RTC becomes device 8 and the MCP is device 9. Very simple circuitry addition there, but let's go and see if we can modify our code to support that. Right, so let's see if we can make the code any neater with this. Got quite a few places to change it. Now, this horrible way I set this, it was inverted for everything. So this one is setting the clock and no chip select line. Unrolling the loops like this does work wonders for performance, but it makes maintenance quite painful. Need to double check the code on those. They can't both be right, but the device is probably tolerating it. So the chip select is high and clock and data are low. That is 0. Okay, so 2 out of my 3 functions start with a high clock. So I'm guessing I just made the mistake on this one. Actually, let's do that instead of 0. Makes the code slightly more readable, even though this is actually a 0. There's actually less code changes than I expected. Let's give that a try. Okay, so that worked, and we've got the simpler output on all these lines. Now I have set all the lines high just to be careful about those selections, which is actually a mistake. We should actually do that. I think I did that at the end of all the code for simplicity's sake. And now we finish with all the bits clear, which is what I was expecting to see. Okay, so I've got another piece of code to look at. Now this just reads the seconds in and outputs them to the console. So I think that's going to be handy for doing some testing. It will also let us confirm I haven't broken things with the change of that starting state. I think that was just a bug in my original code which didn't actually cause a problem. Well, that looks correct. Now we can see on the output lines here, there is just a brighter section on the 3rd bit in our selection. And we know that whenever we've got anything selected, that high bit is set. And we've got just a kind of very faint signal we're seeing on the clock and the data lines. So that's kind of consistent with what we'd expect as well. And on the console, we see a count up, which is indeed lining up with seconds. So let's go back and look at our plan and see where we've got to. So the chip select line we solve with a 74138. Now the output from these devices, we have to assemble the bits one at a time by shifting it into a register. That's what we're doing here. We pull in 8 bits from the GPI data register, and of course that overwrites whatever we had in A. We shift it right by 1, grabbing that data bit in the bottom, and then we shift D left by 1, which uses the logical carry bit to take that 1 bit and stick it into the bottom of D. We repeat that process 8 times, and we have assembled our full byte. We know from other work we've done, there are chips that can do this work, a shift register. So let's have a look at using one of those to pull that data in. Right, so I've got a 595 shift register here, and let's have a crack at using that. This is the same shift register I've used before in a variety of other circuits. As always, we're going to need power and ground. So we've got a master reset. Now that's active low, so we want to pull that high. we have a clock for the shifting, and in the data sheet, this is going to shift a bit in on a low to high transition. Now here's a problem. We're using SPI mode 1 for the RTC chip, and that wants us to read a bit in during a high to low transition. So we need to pass that through an inverter. Fortunately, we've got loads here in the 74LS04. All right, then we've got a latch line. I'm just going to fire that off the same clock signal for now. An output enable. Let's just pull that low. And then our data inline. The outputs are kind of opposite way around than would be convenient for us. And they're split between Q0 over here and 1 through 7 over here. So I've made up this cable that makes things a bit easier. Right, I can see some counting going on there. But the top bit is always set. That's probably not what we want. So if we look back here, we're going to read a bit in during a high to low transition because we're inverting before we feed it into the shift register. So that shift register will grab a bit at this point. Instead of issuing the latch off the clock, we should actually just latch when we read from the register, the same as we did from the 574. Okay, that looks like it's working. Of course, we haven't actually changed any of the fundamental working of the code or circuit. We've just kind of got a shadow copy of the data read in. But if we replace the data that we output to the bus when we read with this, we can avoid all those individual 1-bit reads and all the shifting in the code. And I think that's going to be a significant improvement for us. But let's take a quick look at this on the oscilloscope before we start making that change, because I want to be able to make some before and after comparisons. Right, so I'm going to start with putting the chip select onto the yellow line, and we can trigger that to nicely frame it. And let's grab the data onto the purple trace. That's pretty nice. I've got a good idea though. I'm going to use the external input, put that on the chip select. So now it frames in the same way, but we've got the yellow trace spare to have a look at everything else. So I want to see the clock as the RTC chip sees it. Now let's have a look at the clock that is seen by the shift register. Now, of course, what we want to see is a nice clean alternation between where the transition on the shift register from low to high is in the middle of where the data changes, but it's actually way over towards the start here. But that's just because our clock signal is very imbalanced, because our code has several cycles of work between the clock generation and then pulling the data in. And of course, that's the thing we're going to try and solve here. So, time to make a fundamental change to the circuit. This latch chip is currently responding to a read request from the I/O lines, and let's pull that signal out. That's active low. So if okay, now I've just broken everything there because I let the line float and that was forcing data onto the main bus. So my CPU has stalled out completely. Let's reset that. Okay, so that's working again. Of course, we're getting nothing but zeros. So I've effectively disconnected this latch chip outright. But of course, the shift register's got a tri-state latch in it already. Now this is the output enable. Let's instead take that from the read line. This latch chip's doing nothing. This is doing all the work. Do need to connect it to the bus. And weirdly enough, that started working again, because every time we read, the least significant bit in the shift register is output on the lowest bit. But we don't need to do it like that anymore. Let's go back to the code and see how much it changes. Right, so this is the read function we're calling at the moment. This whole read a bit of data, shift it, we don't need to do anymore. We just need to read it all in once there. Oh, that's cool. Right, let's go back to the bulk input version. So we're taking out 3 cycles. Every instance of the loop. We still need to store it, but we've saved 3 times 8 plus 1 cycles. That's fabulous. I'm doing an immediate load every iteration here, and I don't need to do that anymore because I only did that because I ran out of registers. We were overwriting the contents of A when we did the in operation. So I could in fact initialize A with just SPI CSRTC. And here we want the clock set, so we OR A comma B. So we've added 2 cycles out of the loop, but remove 1 cycle from each bit. Ah, that's cool. Right, let's double check we haven't broken that code. And let's test it out. Fabulous. So this is still working, but if we look on the scope here, that second half while we're reading the data in is much shorter. That's cool. Okay, so we're back here and we can say we have resolved the shifting in with the addition of a 595 shift register. But I think we've got a problem, and that problem is with the clock. You would have noticed when I made the changes to the code there, but I didn't fix the MCP version, and that's because I can't with the circuit as it stands. We've hardwired the relationship between the clock and what we're expecting our internal data collection to do, and that was one of the pieces of code that changed between mode 0 and mode 1. So we need to address that before we move on. Ignoring the other elements of protocol difference between the RTC chip and the MCP chip, this opposite phase of the clock is a significant difference we have to deal with. And in terms of what we want the shift register to do, the difference between loading on a high to low transition as it is at the moment to working on a low to high transition for the MCP chip, which is of course what the shift register actually does before we inverted the signal. So what we want to do is make that inversion conditional, and we're going to do that by adding a control line. Now, I want to change the way we've done this. At the moment, we are sending the software generated clock to the output device, and then we're adapting the signal for our internal shift register. But I actually think we would be much better off doing the opposite. So instead of setting the clock line here, we'll set the clock invert line, which will automatically set it high when the clock is low. We want to set clock invert everywhere we set RTC. We don't set that for MCP. And then we invert all of our actions on the clock. Don't think this line's actually necessary. I think that's how we've left it here. So the logic here, the way we've inverted it, is a little bit funny because we set the clock, then clear the clock. Then the MCP code is unchanged, but once we've made that change to the circuitry, it should start working again. So our clock invert line is bit 2, i.e. the third one along. Right, let's take a look at the circuit. Right, so at present, the clock line is going through one of the inverters, and we want to put a stop to that and drive it directly. But then we want to conditionally invert the signal that goes off to the devices. So I think we need a different chip instead of this 04. 74LS04, that had 6 inverters on it, and I'm going to swap that directly for this 74LS86. Now this has got 4 exclusive OR gates which you can use as inverters, specifically conditional inverters. So we still want this original one to be a basic inverter. So rather than just a single input and an output, it's got a second input here. So I'm going to pull the first input high to make it always invert that signal. Now I'm going to drop these clock lines that go to the 2 devices. Let's put them on the output from that exclusive OR gate. I'll take the input from the clock line as we use it. I'll drive the clock line to our shift register directly, and then the extra input will be from this data line. Wish I had more colour varieties to make this simpler. It's clock related, so I'll make it yellow still. So in theory, this should work exactly the same if we've made the correct change to the circuit and the code change. And that does indeed appear to still work. Now, one thing that's evident looking at the scope trace now is the data read is notably quicker than the data write where we're selecting the address at the start. Let's check our full clock, see how that looks. Looks like we've broken that. So it looks like a lot of the correct stuff going on. Right, let's go back and look at the code. Right, I can immediately see a problem here. When we're writing the address, we're correctly setting RTC and clock invert and the clock, but then when we switch to reading, we're dropping the clock invert bit. You know, I could argue I should just create a value that combines CSRTC and clock invert. But obviously I'm going to gradually evolve this code into something that's much more generic, where you specify a device and the mode and then perform read and write operations. And so we'll be kind of evolving this code away from needing that kind of hack later on. All right, let's have a quick test of that. Okay, that still doesn't look right. Ah, that's a really obvious mistake. So I've unrolled this loop, so it's totally fine to just set A to the correct values at the start of the loop, but I do an in operation here to actually read the data in, and then I loop back to here, so I've overwritten the contents of A. So that needs to happen inside the loop. Obviously the first time round I could actually just load the value with clock cleared, but for the time being I won't do that because I prefer for this loop unroll to be 8 copies of identical code, because we're not done changing it yet, I don't think. Bingo. And the time's fairly accurate. And the annoying thing, of course, for me of writing time-based code is you get to see how actually long it took me to do that, as opposed to what I edited it down to for the final video. Right, before we move on, let's take stock of what we've got. So now our loop is 2 cycles, 4 per bit. We read in once and store it, that's 3 cycles, then the same loop structure. So we have roughly doubled the speed of this by replacing 2 chips and adding 1. I'm pretty pleased with that. Now we could even increase the speed of this further because we're switching in these loops between 2 values for the clock. If I added an instruction to the system to support out GPIO, B, we could just store the two values in A and B, and that would double it again. That would be a significant improvement, but that wouldn't help us with the output stage, where we still have to do a bunch of extra shifting to modify the data in there. Okay, that's actually some pretty good progress. We've just about doubled the speed of the circuit when reading data. We've added some hardware support for the chip select lines, which also simplifies the code. We've added a little bit of extra functionality for helping us to invert the clock when necessary. And we've added a shift register to deal with pulling data in from the external SPI device. In the next video, I want to look at improving the generation of the clock signal and also doing a similar kind of functionality for handling shifting data out to the SPI devices. And that's going to see an awful lot of additional functionality added to the system. Well, as always, a big thank you to all my patrons. I appreciate the support, and I really hope everybody found this video interesting. And I will see you again soon for the part 2. Goodbye.